This talk is on Metakaolin in concrete, and specifically on the role of alumina. There are many different classification systems for natural pozzolans, some for pozzolanic materials. Some are very complicated, like this one. It's quite simple. It splits pozzolans into natural and, if you like, unnatural pozzolans. And the natural pozzolans are split into raw and thermally activated pozzolans. And today we'll talk about this session. In my presentation, we'll be talking specifically about metakaolin, which is a calcined, relatively pure kaolin clay. A lot of the data that I'm going to be showing, before I get there, we've seen something like this slide a couple of times today already that shows the ternary composition of different pozzolans. And today we're talking specifically about metakaolin, but making a comparison with silica fume. And the reason that I'm doing that because of the great difference in the alumina content between silica fume and metakaolin. And there is, in fact, a mistake in that slide. Silica fume is 95%, is typically over 90% silica with very little alumina, whereas metakaolin is typically about 55% silica and 45% alumina. I'm not quite sure what happened to that slide. There is, of course, a significant difference in the particle size distribution of these materials. The metakaolin I'm talking about mainly is in the D50 value of around about 2 microns. But silica fume is reportedly in the region of 0.1 microns, but it's rare that you get fully dispersed silica fume that's really that fine. So rarely does silica fume really achieve its 0.1 micron average particle size. I'm talking specifically today about the 3 different durability mechanisms where we're going to look at the resistance, the chloride penetration, we're going to look at alkali-silica reaction, and we're going to look at resistance to sulfate attack. And with sulfate attack, we're going to be talking about exposure to external sulfates and also heat-induced expansion due to delayed ettringite formation. The testing that we've done a wide range of testing with metakaolins and other pozzolans in the past, but a lot of the testing we do is based on the ASTM C1556 bulk diffusion test, where we soak discs of concrete in chloride solution for various periods of time and then profile them. And we look at the chloride content of those profiles. So you can see the test method on the left. And on the right, we can see typical profiles for concrete, 0.4 water cement ratio. And these are after 40 days of soaking. And what we're seeing is a good comparison between concrete containing 8% silica fume and about 12% metakaolin. Our research shows us that 12% metakaolin gives you similar permeability as 8% silica fume, certainly at early ages. And you can see on that slide as well the results of rapid chloride permeability testing. The coulombs passed after 6 hours are very close for these mixtures. What we do see with the passage of time is we start to see that metakaolin provides significantly enhanced resistance to chloride ion penetration over silica fume. We also have data now for 4 years, which I try to include in this presentation, but I recently got the data. But we can see here, again, very similar rapid chloride permeability test data. If we looked at the ionic conductivity of the pore solution and determined what the formation factor for these concretes would be, it would be very similar. And yet the metakaolin is providing a much enhanced resistance to chloride ion penetration. And that's because one thing we don't include in the formation factor or any of our electrical resistivity tests is the impact of chloride binding. And we can see here some results from chloride binding from one of my mine and Doug Hooten's PhD student, Hassan Zabara, showing the bound chloride plotted against the free chloride for 4 different mixtures. Hassan tested a much wider range of mixtures than this. I'm just showing a comparison here. And we can see that metakaolin is by far and away has a much, much higher binding than either fly ash. Well, I'm not showing data for slag here, but it's the same for slag and for silica fume. Silica fume tends to reduce the binding capacity of the Portland cement, whereas metakaolin significantly enhances it. And that can be attributed mainly to the formation of Friedel salt. And what you're seeing here is X-ray diffraction results for pastes that have been steeped in a 3 molar sodium chloride solution. And you can see the much higher peak of Friedel salt for metakaolin than for the Portland cement. And the silica fume has the lowest peak for Friedel salt. And in fact, to a certain extent, you can almost predict the peak intensity of the main Friedel salt peak based on the alumina content of the binder that you're using. You can see there the considerable increase that results from using metakaolin, relatively high alumina content. So the alumina is very helpful with regards to chloride ion resistance, mainly because of the chemical binding that helps. So we're going to switch gears now and talk about ASR. What you're seeing there is just a data dump of expansion of concrete prisms at 2 years, plotted against replacement levels with various different supplementary cement materials, including fly ash and slag, silica fume, metakaolin, and ternary brands of silica fume in either slag or fly ash. And what we can see is that silica fume and metakaolin are very efficient in this role. Silica fume generally works at about 10 to 12%, and metakaolin works in a similar replacement level. This can be attributed, the ASR prevention that's provided by SEMs can be attributed to their ability to reduce the concentration of the hydroxyl and sodium and potassium ions in the pore solution. And that's shown here, a very similar plot, but now we're looking at the hydroxyl ion concentration of paste after 2 years, plotted again against the SEM replacement level. And here we see the silica fume is slightly more efficient than metakaolin, and that's largely down to its increased silica content. The hydroxyl ion concentration, and therefore the sodium and potassium ion concentration, can be predicted of a particular binder, or the pore solution of a binder, can be predicted based on the chemical composition of that binder. And here's a relationship that I published about 10 years ago now, showing the hydroxyl ion concentration as a function of the alkali content of the binder, but also its calcium and silica content. The alkali content, of course, plays into the alkalinity of the pore solution, whereas the calcium silica content plays into the binding capacity of the hydrates. The higher the calcium, the lower the binding capacity. The higher the silica, the higher the binding capacity. And we found this relationship between the sodium, or I should say the sodium equivalent, the calcium oxide content, and the silica content. And we found that alumina has a negligible impact on the pore solution alkalinity. And this is something that Karen Scribner presented yesterday also. Alumina has an impact on the dissolution of silica, which is beneficial for ASR, but not necessarily on the alkalinity of the pore solution. So here, alumina is taking a backseat. We've been extending this relationship and looking at other published data on pore solution alkalinity. And there's data here from about 300 different tests. My relationship was based on the 79 different tests we did in my own laboratories, whereas now we've added about another 200 data points from various studies. The relationship, the solid line is the relationship that's in my paper from 10 years ago, and it clearly needs adjusting to fit all of the data. But once again, the alumina content doesn't really play a role in the hydroxyl ion concentration for all of these pore solution studies. Again, you can relate binder composition to expansion of concrete prisms, and you get a reasonable relationship, although it's not perfect. And there are a number of very high alkali SCMs that don't necessarily fit on the plot here. They're the few data points you can see down on the bottom right of the graph. But a reasonable relationship between the alkali content and the calcium silica content, a calcium silica ratio of the binder. When you look at the accelerated mortar bar test, the alkali, the role of the alkali that's in the binder actually falls out, is no longer important because, of course, you're supplying an inexhaustible supply of alkalis in the host solution. So really, it's just the calcium silica content or calcium silica ratio of the binder that's important. I should say it's the calcium to the silica squared that's important. The silica playing a more important role than the calcium. We have long-term data for metakaolin. These are some metakaolin blocks that were placed on the BRE exposure site by Ted Sibick in the last millennium. He placed them in the late 1990s. We went back, myself and my wife went back there and took a look a couple of years ago when all of these blocks were approximately 20 years old. And metakaolin at a 10% level of replacement was effective with all three reactive aggregates that were used on this site and at all three alkali contents, at the wide range of alkali contents, I should say, that were actually used. The alkali contents ranged as high as 5 kilograms per meter cubed of equivalent soda. And even at that level with a highly reactive aggregate, 10% metakaolin was seen to be sufficient. So long-term effectiveness with metakaolin. Moving on to sulfate resistance, this is where we start to see the alumina is not necessarily helpful. This shows some data, again, from work that was done in the late 1990s with metakaolin from Cornwall in England, from the English China clay deposits in Cornwall, England. And you can see with a high C3A cement that 5 and 10% metakaolin did not necessarily increase the sulfate resistance, or in fact, didn't increase the sulfate resistance of mortar bars produced with this high C3A cement. At 15, 20, and 25% metakaolin, we did get good protection out to 2 years. So these blends would be classified as being of high sulfate resistance. With a moderate C3A cement, 10 and 20% was effective. We didn't have data at 5%. And also with a low C3A cement, we got reasonably good sulfate resistance as well. But with that higher C3A cement, 5 and 10% metakaolin made it worse. And there's a summary of the data here. L represents low sulfate resistance, which is where you get damming expansion in less than 6 months. M is moderate sulfate resistance. H is high sulfate resistance, and VH is very high. So we can see, provided we put enough metakaolin in there, we can get very high sulfate resistance. But at 5 and 10%, the results are variable. More recently, we found that some mixers, even with 15% metakaolin, have not been effective. This is not with the same metakaolin source. This is a metakaolin source from a supplier in North America. And we found here that 15% metakaolin was not effective. At first, we thought this might be due to the fact that the test method requires you to make mortar bars to the same flow, which means you increase the water cement ratio with metakaolin. So we repeated the test with a super plasticizer and equal water cementing materials ratio, but even then we got better performance, but not good enough to give us moderate or high sulfate resistance. So it depends, the sulfate resistance depends on the source of the metakaolin as well as the replacement level. So what's happening here is with metakaolin, we have a very high alumina availability, which gives us a low sulfate to alumina ratio. And that favors the early conversion of ettringite into monosulfate prior to immersion of the mortar bars in the external sulfate solution. So monosulfate is a predominant phase, aluminate phase, when you immerse these bars. So of course, when you provide them with an external source of sodium sulfate, the monosulfate reconverts to ettringite. There's no longer not enough space to accommodate that ettringite formation. There was initially in the fresh mortar, but not now in the hardened mortar. so we get expansion, cracking. So that's what happens at first. All of the monosulfate converts to ettringite, but then once all of the alumina is combined as ettringite, what we start to see is the second stage of sulfate attack, which is gypsum formation, a reduction in calcium hydroxide, and eventually decalcification of the calcium silicate hydrates. And that's why the mortar bars with low levels of metakaolin actually disintegrate rather than just continue to expand like the control specimen does. I think we can make an argument that mortar bars produced with 15% or more metakaolin, which did show high sulfate resistance. The high sulfate resistance is probably mainly attributed to the physical reduction of permeability rather than an increase in the chemical resistance of the hydrated phases. However, you could make an argument that the increased silica that accompanies the increasing metakaolin content does change the nature and vulnerability of the calcium aluminate phases, perhaps favoring the formation of calcium aluminate silicates, which could lead to a higher chemical resistance, as well as a higher physical resistance. When we look at delayed ettringite formation, the alumina plays a different role. Instead of increasing the vulnerability to attack, increased alumina, as we'll see, actually prevents damaging delayed ettringite formation from happening. I'm going to show you some results here for mortar bars that were cured at 95 degrees Celsius for 12 hours prior to long-term storage in lime water at normal temperature. And you can see what happens to a very temperature susceptible type 3 cement here, high early strength cement. At 95 degrees Celsius, you get very early age expansion, a massive amount of expansion. We can see the role of the curing temperature there. At 80 degrees Celsius, the expansion is less. At 70 degrees Celsius, it's less again. And at 60 degrees Celsius or lower, we don't see any heat-induced expansion. So ambient temperature DEF is a myth. And we've published ourselves, and other people published papers to demonstrate that. What happens when you blend that type 3 cement, that same type 3 cement with metakaolin, is even a small amount of metakaolin just kills the expansion. Even out to periods, and I think we have longer term data, at least observational data, if not actual expansion data, that goes out to 4 or 5 years. A small amount of metakaolin is sufficient to completely kill expansion. Silica fume, on the other hand, is not able to do that. I didn't mention before, I forgot to mention earlier, with the external sulfate attack, 8% silica fume was very effective at preventing expansion, probably mainly due to the reductions in permeability, but perhaps again due to a slight alteration of the calcium aluminates to calcium aluminate silicates. But here we see silica fume is not effective, even at 15%. And the reason for this is the silica fume does not contain alumina. That's the main difference between these two SEMs. Looking here at the amount of ettringite that forms during long-term storage here, we cannot explain the lack of expansion due to a reduction in the amount of ettringite that forms. The ettringite forms regardless of whether you have silica fume or metakaolin present. The difference is where it forms. In the absence of metakaolin, with straight Portland cement mixes or silica fume mixes, the ettringite forms within the small pores in the outer hydration product, and this causes expansive stresses to form. You can see the ettringite growing in little nests here and gaps opening up around aggregate particles. When we have metakaolin present, we don't form ettringite in the paste. We form massive amounts of ettringite in pores and gaps and cracks that already exist in the mortar sample, but not within the paste. And this is not accompanied by expansion. And there's just some words that basically repeat what I just said. So there's some different roles of alumina in the durability of concrete produced with metakaolin. That's all I have to say in the 12 minutes, but if anybody wants access to these publications where this data exists, I'd be happy to provide it. So thank you very much.
Thanks, Mike.